Hello everyone, my name is Ravindulal. I am a PhD candidate in Charleston University, specializing in artificial intelligence. Today I am presenting our paper, When Language Model Guides Vision, Grounding Dinner for Cattle Muzzle Detection. Here you can see the current technology used in Australia to detect the cattle. This technology is called NLIS ear tag. This is an example of electronic identification. These ear tags make managing cattle much faster and more accurate than traditional methods. Each tag carries a unique ID and farm information, and in Australia, the NLIS uses these tags to track every movement of cattle, and it is stored in a central database. This helps with traceability, biosecurity, and overall farm management. But it's not a perfect solution because ear tags can get lost, damaged, tampered, or vulnerable to the attacks. Then what is the best solution? Again, muzzle patterns are the best solution to the existing analyze ear tag. Each muzzle pattern is unique, just like a human fingerprint, and it never changes throughout the life. The use of muzzle patterns just require a clear image of a muzzle. With the advancement in computer vision and artificial intelligence, these muzzle patterns are analyzed by advanced algorithms, and they are similar to the facial recognition for humans. This makes muzzle recognition a fast, economical, and highly reliable method for identifying individual cattle in the farm. It has a huge potential to improve farm management, enhance livestock traceability, and make identification easier and safer for both farmers and cattle. The first step of development of muzzle-based identification system is the detection of muzzle from the image. The basic pipeline for muzzle detection is shown in the slide. It looks very simple. The existing models like YOLO or CNN are used currently to detect the muzzle using the presented pipeline, but there are some challenges or difficulties. This research aims to provide alternative solutions to detect the muzzle and also solve the challenges that are presented in the existing algorithms or the technologies that uses advanced deep learning models like YOLO and RCNN. The first major challenge is collection of good quality muzzle images on a real farm. In the real farm, the lighting changes, the movement of cattle, and different camera angles, also the busy background and occlusion, make it hard to capture clear and consistent images. The second challenge is the limited data. Deep learning models require thousands of labeled images, but collecting large datasets is very slow, costly, and also difficult in the real farm environment. The third challenge is requirement of the annotation or labeling. Labeling muzzle regions accurately takes time, expertise, and also need a careful attention. In a real-world farm, farmers are always looking for a simple solution, and most of the farmers, they are not an expert in computer science. Another challenge is that model trained on one type of data cannot be utilized in another settings, breed or location because of the poor generalization. The solution we explored here is the combination of language and visual features. This is also called zero-shot muzzle detection. In this approach, we don't need to label or annotate the muzzle images. This works directly with the combination of natural languages, which is also called prompt, and the input images. The input to the model is a pair of the images and the description of the image. The model extracts the image and text features using the architecture called encoder. These features are mapped and the decoder provides the correct location of the muzzle, which is shown in the figure. The red bounding box is detected muzzle, and using the zero-shot based muzzle detection, the muzzle doesn't require to be precisely annotated, and the model doesn't require to pre-train or train the models. Here on the screen you can see the high-level pipeline of our research. We begin with data collection and followed by pre-processing. Then we move on to the fine-tuning geoset models. After carefully evaluating their performance, we identify the best approach. This pipeline provides a clear, efficient path from raw data to a robust and fully automated geoset muzzle detection system. To the best of our knowledge, this research represents the first attempt to implement geoset detection in the domain of cattle muzzle identification. For this study, we worked with 3 diverse datasets to cover different environments, camera setups, and cattle breeds. These datasets are shown in the table. As shown in the table, CSU data is the dataset that we have captured in the Charlestown University's Global Digital Farm. The rest of the 2 datasets are the publicly available datasets. The second step in our approach is to prepare the ground truth data of the muzzle. To achieve this, we used RoboFlow to annotate the muzzle regions in our cattle. These annotations were only used for the evaluation, which provides a robust and precise benchmark to assess the accuracy and effectiveness of the geoset muzzle detection models used in this experiment. But in the real application point of view, we don't require any sort of label dataset. The next step was to choose the right geoset detection models in our task. On the screen you can see the table summarizing all the models that we have explored. Each model brings unique strength, and evaluating them helped us to find the best fit for detecting cattle muzzles accurately and effectively. We used mean average precision to evaluate the model's performance. The next step in our workflow started with choosing the right language prompt. We began simply with cattle muzzle and then step by step adding more descriptive details to capture the unique features of the muzzle. At each step, we measured and evaluated the performance using mean average precision at 0.5, which is MAP at 0.5. We carefully tracked each prompt, and on the screen you can see the table showing all the prompts we tested and their corresponding MAP scores. From this process, we identify the best prompt for the most accurate muzzle detection. The performance of the best model is shown in the table. The results summarized in table 4 reveal the grounding dino is the best one. It consistently outperformed all the models across all thresholds, providing itself as the most reliable and accurate choice for geoset muzzle detection. All the models used the same images and with the same prompts. Here you can see the demonstration of our pipeline for the muzzle detection. As you can see on the screen, the system works across different datasets, and without training on any images, it is able to accurately detect the muzzle with a bounding box. This approach provides a flexible and efficient way to isolate the muzzle. Once the muzzles are detected, the muzzle can be used in multiple ways for cattle identification. For example, it can be automatically cropped to prepare the data for downstream identification tasks, making the entire process faster and more scalable. Here you can see when we applied the geoset muzzle detection, and this only requires to upload the images of the cattle. The system will automatically detect the muzzle, and which is provided by the red colored bounding boxes. As you can see, the muzzles are accurately detected with the red colored bounding boxes. We have used all 3 different datasets used in our experiment. In the demonstration, you can see 3 different datasets. 3 different datasets here. This is the last dataset that we have used. And here you can see we can just upload the module and the model is processing. After processing the model will provide the red bounding boxes with confidence score and also the name of the module, or just yeah, the name of the class, which is module. Here are some more sample of the detected modules. The samples of the detected modules from each datasets used in our experiment. The red bounding boxes show the modules area in the image. This slide compares the performance of existing YOLO-based models with the number of the labeled images used. Grounding Dino achieves impressive zero-set results without any fine-tuning or additional training. In contrast, YOLO variants require 40 to 80 label training samples to reach similar performance. The slide also emphasizes the practical advantages. Fine-tuning YOLO models requires significant time, computational resources, and manual effort, whereas grounding Dino provides a scalable and cost-effective alternative which shapes data annotation cost, time, and effort, followed by model training cost and effort as well. Um, uh, our approach provides a straightforward solution for implementing a model-based cattle identification. This study highlights the potential of the prompt-driven zero-shot detection models for scalable and practical livestock monitoring applications. Yes, there are some limitations of zero-shot models, which should be carefully handled. Limitations include the large language models are susceptible to the hallucinations and prompt sensitivity, which should be handled carefully. This slide presents the references used in the earlier slides. Thank you for listening and the presentation that I have shown. If you've got any questions, you can scan the QR code on in the slide. Thank you.